We've all seen it after a storm, a massive band of colors arching across the sky, apparently anchored somewhere over the horizon. It looks like a physical structure, something you could chase down and stand right underneath. But as you walk toward the arch, it retreats. It maintains a constant distance from you, hovering perpetually out of reach. You can never reach the end of a rainbow because it has no physical end. It occupies no actual three-dimensional space in the sky. The rainbow is a viewing angle phenomenon. It is a real-time geometric event that requires a specific relationship between the sun, the rain, and your own eyes. From a high vantage point like an airplane, the arch reveals its true geometry. Without the ground obstructing the view, the rainbow appears entirely circular. To understand how this geometry functions, we must look past the macro view of the sky and focus on the precise behavior of light inside a single drop of water. We'll start by scaling down to a single spherical raindrop suspended in the air. Sunlight enters the droplet as a beam of white light. Because water is denser than air, the light slows down and bends, a process called refraction. This bending causes dispersion. Each color in the spectrum has a different wavelength, so each color bends by a slightly different amount. Red light bends the least, while violet light bends most. After separating, the light strikes the curved arc surface. It bounces off the interior wall, reflecting toward the front. As the light exits, it speeds up and refracts again. This concentrates the light at specific exit angles, 40 degrees for violet and 42 for red. Every raindrop in a storm acts as a microscopic prism, firing these specific colors at predictable mathematical angles. Zooming back out to a person on the ground, your shadow marks the anti-solar point, the center of the entire geometric event. Because red light exits the drops at a specific angle, you can only see it when a raindrop is situated precisely on a 42-degree cone expanding from your eye. The arch we see in the sky is the collective output of trillions of different raindrops, all occupying that same angular position relative to your pupil. Occasionally, a second bow appears outside the primary one. This happens when sunlight reflects twice inside the raindrop, before exiting, emerging at a wider angle between 50 and 53 degrees. This double reflection reverses the color order and leaves a conspicuous gap between the two bows. Known as Alexander's dark band, this is a region where the raindrops are not scattering light toward your eyes. This geometry means the rainbow isn't just a thing we look at, but a specific alignment of light we are perfectly positioned to intercept. Because the apex of the 42-degree cone sits inside your pupil, the entire rainbow is anchored exclusively to your perspective. If a friend stands right next to you, they occupy the center of their own unique cone. They are seeing light from an entirely different set of raindrops. Even your own left and right eyes receive light from slightly different drops, meaning each eye perceives a technically distinct rainbow. Viewing a rainbow is a solitary experience. It exists as a private optical performance that no other observer in the world can share. Every second, the millions of falling drops that create the image are pulled toward the ground by gravity. The rainbow you see right now is formed by completely different water droplets than the rainbow you saw just a few milliseconds ago. The arch maintains its appearance through a constant cycle of renewal. As falling water enters your optical cone and exits again, the image is perpetually replaced by the next wave of rain. This makes the sky function like an active, real-time collaboration between solar radiation, the falling water, and your own biology. The colors only align when your eyes occupy that specific physical coordinate. If you move, the old rainbow vanishes and a new one takes its place.